understand signaling pathways and how signals can be disrupted chemically, and they can. So this is an overview. You have to understand the physiological concept of an action potential. You have to understand how ions move here. You have to understand the role of neurotransmitters, and you have to understand receptors. These are all critical concepts to understand pathways. In the next exam period, we're going to be talking about a lot of pathways. We're going to talk about what is a pathway. Within the brain, we talk about white matter and gray matter, and how white matter is overwhelmingly myelinated fiber tracts. Okay. That's easy to understand and simultaneously easy to be confused. It's hard to believe that there are parts of your brain that have almost no cell bodies. Almost everything that's white in your brain is mostly axons, myelinated axons. And it's easy to attempt to visualize what a pathway is. It's that physical group of axons moving through. But then we talk about reinforcing pathways. Have you heard about that? When you practice something, you're reinforcing a pathway. When you first learned how to walk, and my guess is none of you have any recollection of that, but you may have interacted with little kids that are learning how to walk. And their first attempts at walking are really brutally awkward and painful to watch. And you're sitting there, oh no, do this. And no matter how many times you say do this, they can't. And the reason they can't is a pathway, while physically present, while those axons are present, that pathway and its neurochemistry are not optimal yet. So you decide you want to get an A in a class. Now, when you make that decision, it's like learning how to walk. Have you ever had a class where you came in and you kind of stumbled around for a while? And then as the class progressed, you got better. Or playing a musical instrument. Maybe you play a musical instrument? Yeah? All right. So the musical instruments are in the back row. The rest of you do not want to admit to it. All right. Well, when you start playing a musical instrument, I believe the technical term to describe you is that you suck. All right? Nobody picks up a musical instrument and sounds good in the beginning. And then what do you do if you really want to play that instrument? You practice. And what is practicing? Practicing is building up and developing pathways. And what you're doing is you are chemically reinforcing the pathway. So we're going to be looking at these things for the next few weeks, talking about them. But to understand what goes on, you have to understand what's happening here. So let's blow that up a little bit. All right. So here we have an axon. This axon is called presynaptic, as it is approaching the synapse. Now, the reason we have to designate an axon as presynaptic, whereas you might just think about it, well, an axon is taking a signal somewhere. Okay. But sometimes an axon will take a signal to another axon. So you can, in that scenario, have a presynaptic axon and a postsynaptic axon. This axon is from the presynaptic neuron, and the target is the postsynaptic neuron. This structure is the synapse. The synapse, in essence, is that area where the signal moves from one neuron to a target. That target can be a neuron. In this case, it is a neuron. That target in the neuromuscular junction, as we talked about last week, would be a muscle fiber. That target, if it was the autonomic signal going to the adrenal cortex, or adrenal medulla, I forget which one does it go to. Medulla? Is that a guess, or is that a... I got it.
This is a guess.
No, it's a good guess. Okay? But in that case, the signal going to the medulla is going to interact with a glandular cell. Okay? So the target can be a neuron, it can be a muscle fiber, it can be a glandular cell. Now, you want to talk about action potentials at all? Yes?
A little bit.
A little bit? An action potential. We are talking about the charge on a membrane, the charge on the neurolemma. The neurolemma is the plasma membrane on the outside surface of a neuron. And pretty much that's going to be what we're talking about. Under normal circumstances, all of your neurons have a resting membrane potential, RMP, of -70. We'll talk about how that's maintained. With an action potential, the charge on the membrane potential is going to change. We're going to bring about a change in that signal by using channel proteins. We'll get to that. Let's just talk about the millivolts involved. So we're at -70 millivolts. As we move, mostly sodium ions initially, but some sodium and some potassium ions, we are going to create this. A graded potential. That graded potential is a slow and reversible depolarization. So the charge on the surface is becoming less polar. So we call it depolarization. Once we get to a charge of -55 millivolts, we are at threshold. Once you hit -55, an action potential will take place. And that's this. potential is two things. It is irreversible, and it is all or none. It's either going to happen or it's not going to happen. Once we get to minus 55, this whole event occurs. So are we okay so far? All right. So that's our action potential. We have kind of three phases in here. Depolarization, repolarization, and this time period in here, which is hyperpolarization. You go beyond minus 70, you go minus 75, minus 77, somewhere, and it's slightly variable. We'll talk about that. Okay? So are we okay with the concept here of an action potential? All right. Well, this is a typical motor neuron. The action potential is traveling along the surface of the neurolemma of the presynaptic neuron. That's what these purple arrows are meant to show you. As it approaches this, many names, the axon terminus, the axon knob, you'll see them both in use. I tend to use axon terminus. You'll also hear it referred to as the synaptic knob, so lots of names. As the charge gets down here, these calcium channels are going to open. Those calcium channels are integral channel proteins in the neurolemma, in the external plasma membrane of the neuron. And they are what are called voltage gated. The gate has the potential to open and close. Voltage gated means with a voltage change, they open. So as the action potential comes along here, we depolarize, they open. As they open, calcium enters the axon terminal. This is going to bring about a number of changes in the chemistry of this terminus. And these, which are these synaptic vesicles, are going to migrate towards the surface. This is all. Remember, this is a three-dimensional structure. Okay? So that axon terminus is sitting there kind of like this, sitting in the synapse. These vesicles are produced further up, and they contain neurotransmitter. They are going to merge with the plasma membrane, and the neurotransmitter is going to be released into the synaptic cleft. The synaptic cleft is the area here between the presynaptic neuron and the target. Are we all still okay? This is a great, you might be a little removed from all of this, and it's a great time for you to ask questions. So stop me anywhere along the way here and say, Kel, wait a minute, I'm a little bit lost. Okay?